We will talk today about our new UnRisk-Q Instrument Builder. It's a new interface to our quant finance software. This is Michael Aichinger and Sascha Kratky from Unisoftware Plus GmbH in Austria. And UnRisk is made by a consortium of our company and the Math Consult. So we will switch now and make the general part of the talk. We will talk about this architecture of new UnRisk, and you have a user view. When you are a quant or when you are working in a bank, you have this term sheet view, meaning that you have a PDF document which can be 100 pages, where you have the information how your financial contract is built up. And there's a great deal of flexibility required. Why? There are many, many different of these financial contracts, and there can be very simple things. And for example, an annual fixed rate bond is really simple instrument. And there can be very complex instruments. For example, inflation, FX linked, interest rate, commodity, equity, all kind of linked instruments, highly structured with auto call features, with call put features, everything you can imagine. And if you want to make a good piece of software, the software should be as flexible as the input should be. This means simple things should be simple and complex things should be possible. On the other hand, you have the hardware view. In the hardware view, you have basically some arithmetic operations, and you can do these arithmetic operations with arrays of numbers. And this becomes even worse when you think of the new hardware. When you think of programming a GPU, then you are on a very low-level programming interface. So on the one hand, you have this very high demand on flexibility, and on the other hand, you have a very, very rigid view on the hardware, how you can program it. And now we tried to connect the dots with our new interface. We had our old interface, which works great. Some of our audience are using it in their companies. And the problem is, as good as it is, it has not the flexibility to fulfill our actual demands. So what we did is we introduced a more layered architecture. We call it interface layer, and this interface layer is now a Mathematica layer plus a C++ layer. Then we have an intermediate layer. We call it event stream layer. What we do is we transform each instrument you can imagine into a subsequent event stream, meaning basically, an instrument is nothing else. You have dates, and then certain dates there's a happening or an event. Yeah? And so we transform each instrument in something like an event stream, and then we have a hardware layer. With this event stream layer, we go to the hardware, and what we do is basically then arithmetic operations on arrays of numbers. And this hardware layer, we restricted ourselves to a more rigid construction of our numeric algorithms, meaning what we have is QMC and final element solutions, and we get rid of all the other numerical things we had up to now, because up to now we did it. You want to include a new instrument, and we write the whole solver for this instrument, and this is a lot of work, and it's not flexible enough. And now we try to make a very general view on the numerical algorithms, and through the event stream we have the right interface to fill the numerical algorithms with the information. So what we make is the user input is transferred to our intermediate representation called event stream. Then the event stream is transferred into the different hardware representation. What we want to support, or what we support, is a different structure in parallelization. So we have coarse-grained and fine-grained parallelization, meaning a single instrument can be parallelized on a node. You can calculate the instrument on the GPU, you can calculate the instrument on your multi-core architecture. And a portfolio of instruments, or when you make scenario analysis, you can spread the calculations within your cluster, within your supercomputer. So this is the coarse-grained parallelization. And we try that all of our numerical algorithms support the fine-grained parallelization, so that on each node we can get the best efficiency. So we tried to decouple our competing demands, a user-friendly interface and a fast implementation on different hardware. We call it a compiler for term sheets. From the software point of view, we have the user interface, and we use, again, as a domain-specific language, Mathematica. We think this Mathematica is a really great platform to build solutions for different types of vertical markets, because there's no other programming language which makes it so easy to use commands which are in the specific language of this vertical market. For an example, I'm doing another project for steel casting industry. There, I use the same numerics at the bottom because it's solving PDEs with finite elements. But there I say, okay, make roll pass process. Is the Mathematica command they use. Here I make solve Black's coal, solve Hall white equation. Same numerics, but different language, meaning that you can use the language your customer is used to. And this makes it much more easy for the customer to feel that this is the right product for him. We have built our Mathematica interface on top of a C++ interface. This is making heavy use of builder patterns and key value stores. Our whole new UnRisk is built on these key value stores to store all information in so-called property list. Then we have the event stream layer. This is C++, where we make extensive use of the Boost library and all sorts of templating and some quite heavy C++ stuff. And then we have the numerics layer. This is basically C mixed with C++, and it makes QMC, finite elements, optimization, solve the inverse problems needed for calibrating these things. So, when you think of the interface, I now present the C++ interface, which is, for example, quite uncommon for a Mathematica conference, but we want to show you how we bring the Mathematica interface down to the C++ interface. So what you can see here is a C++ interface which relies heavily on builder patterns. When you think of the rev rate builder, you build up a reference rate and you make the Euribor 12-month reference rate built with this builder pattern. So you get an object right here. And the other thing I mentioned is the key value store. So what we do is we store each information we need in a key value store, and people can access information about this key value store, so we can put the whole information we have over the instrument, really the whole term sheet, back, and we will try to use a unified language for it, which is common in financial industry. So this is the basic core algorithm we have developed, and now we show you how we put this information into Mathematica.
So enough of C++ for now. I'm going to talk about how these ideas now translate to Mathematica. If you look at the existing product, which is called UnRisk-Q at version 6, basically here's how you use that product. Let's just, as an example, evaluate a fixed rate bond. First, you start by loading the UnRisk package. Then you have so-called constructor functions which let you produce financial instruments. Here, let's make a fixed rate bond which pays a 4% annual rate, semi-annual rate, and with the start date from 2010-4/10 and the maturity date to 2012-10/10. If I evaluate that line, I get a fixed rate bond object, and I can then easily, using the properties functions, inspect the properties of that bond. And for the valuation of financial instruments, I need market data. This market data is usually obtained from a market data provider or from some proprietary market database that banks have set up. And for example, here I make a swap curve, and before this swap curve can be used for evaluation, it has to be transformed into a different form, which is called yield curve. And through a process called bootstrapping, we produce a yield curve from the swap curve. And finally, we have all pieces we need, and we can now evaluate the bond with the valuation date 2010-8/2, with the settlement date 2010-8/7, using the yield curve, and we want to compute the clean value of the bond. You see here you get the clean value, and basically that's the whole thing that UnRisk-Q is about. Even you set up your instruments, you set up your market data, then you run a computation which can be an evaluation, a calibration, or a value at risk computation, and then you get the results. And this interface has served us really well for 11 years, but it's not as flexible as we want it to be. One problem with it, there are many different instrument types for representing different coupon payoffs. For example, we have a simple fixed rate bonds, but we also have rather complex types, for example, a callable, puttable general constant maturity floater. And let me just bring up the documentation center now. Go to the add-ons and packages, where you find the documentation on UnRisk-Q. And here, for example, when you go to interest rates, you see all the different instrument types that our product supports. The problem with all these different types is that there's no standard naming convention for these type of instruments. Like in particle physics, there's a so-called particle zoo. In finance, you have a financial instrument type zoo. And if you look at the definition of these instruments, for example, the constant maturity floater, you see that the real difference between these different types goes into the coupon function. The coupon function is a function which describes the coupon rate which is paid to the buyer of this bond, and usually, for example, this is since this may be bounded by a cap and a floor, and between the cap and the floor, the coupon rate depends on some observable market data. For example, a reference rate, a yield rate, or an FX rate, or some equity stock price. And let's just look at a different bond type. You see, here you just have a different coupon function, and the problem is all those different coupon functions are mapped to instrument types in our universe. And what we find that it's very difficult for customers who are not familiar with this terminology to translate the coupon function information they obtain from the term sheet into the correct financial instrument type we provide. And so let's go back to the slideshow. What we really want is to reduce the number of types to just a few manageable number of types. And the other thing is that we are now currently in the 11th year of the development of UnRisk, and the code base is starting to show age. That means it has accumulated some crust. It has over 1 million lines of C++ code. It has over 150,000 lines of Mathematica code, and it has, of course, many different developers have over the years added code to that product. It's always much easier to add new lines of code to an existing code base than to refactor the existing code so that less code does more work. One other drawback is it's based on a rather old linking technology, which has now been superseded by newer technologies. This is called MathLink. And for GPU support, which we added 3 years ago, we decided on using CUDA, and CUDA has been surpassed by OpenCL now. The problem of CUDA is that CUDA does not support the CPU, and also it only works on NVIDIA graphic cards. And as Michael already mentioned, we have very complex algorithms. Almost any instrument types needs its own algorithm for doing the computation. So that's where the million lines of code stem from. And we now translate the ideas that Michael talked about to Mathematica. In the new UnRisk, we will only have 3 general instrument types. We'll have a bond, we'll have a swap, we'll have an option, and all instead of having different types, we will have programmable coupon functions. And you will be able to program these coupon functions in Mathematica. And of course, these instrument types can have market data as an underlying, and as we support the following market data underlyings. We support interest rate market data, equity market data, foreign exchange rates, credit rates, inflation rates, and of course hybrids of all those different kinds of market data. We started a new code base almost from scratch. You've seen the bits and pieces in the other slide. And it's very modern C++ code. It's designed to be cross-platform from the very start. It only has a very thin layer which handles all the interfacing to Mathematica. It now uses library link as the linking technology, and it's largely based on algorithms which work very, very well on modern hardware. When UnRisk-Q was designed 10 years ago, the hardware space was completely different. We lived in unicore age. Now we live in many-core age. So now you have to use algorithms which really are easily parallelizable on modern hardware like GPUs and many-core machines. And that's where Monte Carlo simulation, which was not really doable 10 years ago, is now such an interesting algorithm. And the new interface design is based on two types of data categories. The first category is the so-called UnRisk Builder. Its task is the construction of data, and it maintains a mutable state, and the mutable state is represented as a key value store. Once the constructed thing is called UnRisk object, and its task is the representation of some constructed thing, and this one is immutable. You see that mutable state should usually be avoided, but mutable state can make sense if it is contained in a very narrow space, and with the builder pattern we can do that. For the new language syntax, we decided on using J-Link style syntax because we find that this kind of syntax is much more accessible for our customers who are experts in the field of finance, but who are not very experienced Mathematica programmers. And usually they have some programming background in an object-oriented language, and they are very familiar with the notion of an object that receives a message, and then the message has an argument. And with the add operator, we basically mimic J-Link's style syntax here, so you can chain different method invocations, and then finally you have the call to the build method, which produces the final UnRisk object. How do we use library link in the new UnRisk? Library link is used as the glue code between the Mathematica kernel and the UnRisk shared library. Basically, all data lives in the UnRisk shared library, and on the Mathematica kernel side, you have symbols which basically act as references or pointers to the data which is hosted in the UnRisk shared library. Let's just look at a complex example of the new interface. Let me just quit the kernel to start from a defined state. I now load the new UnRisk package. New UnRisk is the working title we use. This, of course, will be then just UnRisk when it's released. Let's just look at the names that we have available here. The first thing to do now is set up all the builders that we need for our example. We have a ref rate builder, a fixing builder, a coupon builder, a numerical parameters builder, a Hall-White model builder, a bound builder, and finally a valuation object builder. And you see this output here is actually debugging code I left in for you to see how the Mathematica code interacts with our UnRisk shared library. So each line means that a function that is exported from our DLL has been invoked. Okay, now let's just set up the reference rate. You see the reference rate, I construct the reference rate by chaining different property invocations to the ref rate builder, like for example the ID or Euribor 12M, the currency, the rate type, the frequency, the basis, the tenor, and finally I call the build method. You see this called some C++ function exported from our UnRisk shared library. Then for reference rates, I need a so-called fixing, which basically defines when the rate is fixed for the simulation of the instrument. And finally, I can now set up a coupon function, which is set up as a Mathematica function. You see here we have basically the same thing you saw in the documentation center. You have a cap here, and you have a floor. And of course, between the cap and the floor, the rate is fixed through a simple linear function. And once I've set up the functions, I can now define a coupon. and give the coupon the name of my coupon function in Mathematica, and also I have to pass the information on which observables should be passed to the coupon rate function. Here we only have one observable, which is the rev rate we constructed before, and the rev rate will be observed at the fixing we define. Now we set up the coupon. Then we need some numerical parameters like the number of passes we are going to compute, the maximal timestamp, and we build this thing. Then we do not use market data. We use a model for the computation of the value of the bond. And you see here these parameters are basically define our model. It's the initial rate, the drift, the speed, and the volatility. These can also be obtained usually from market data. Then finally, we have to set up the bond we are going to use. Here you see, for example, we have a start date, we have a maturity, the business day convention, and please note that here we passed the coupon structure we defined a few lines above, like here. This goes into the definition of the bond. So that's how the bond is connected to the coupon function. We then have a bond, and finally, from all those bits and pieces, we compute a so-called valuation object, which puts together the model, the instrument, the valuation date, settlement date, and the numerical parameters. And then finally, we can finally run the valuation, and the valuation produces a result container, and it was pretty fast, but what the valuation actually did, it called our coupon function, which is a Mathematica function. And I can now, for example, obtain the result, which is the clean value from the result container. Let's just try a different coupon function now. I can now scroll up and simply copy the definition here. Let's insert it here, and I simply make some changes to the cap and the floor. For example, I use 0.1, and the floor should be 1.0.
No. 0.1.
Oh.
A 0.01 or something like this. Let it by 0.
Okay, 0.
Yeah. Otherwise, you will get nothing out.
Okay. And now, of course, when I run the evaluation, now it will use the updated version of my coupon function, and we should obtain a different result. You see, the result has slightly changed. So what this actually means is that now by simply changing your coupon function, you can basically change the whole definition of the bond. Usually the coupon function can be easily obtained from the term sheet. You just have to translate the mathematical notation of the coupon function to the actual Mathematica code. And with the old interface, if you want to change the coupon function to a different one, it often meant that you had to set up a completely different instrument type, which was very cumbersome. You do not have to do this now with the new interface. And finally, this is the last slide. As a company, we try to focus on our core strengths, and we do not try to diversificate too much. We try to offer the best solutions for the problems that our customers have. And the new design will also enable us to support alternative interface languages. We are simplified via technology called SWIG, which is a simplified wrapper and interface generator, which generates automatically interfaces by parsing the C++ code for different languages. For example, Python is one target language we consider because it's very popular in the finance community. And of course, we'll also add import and export via XML. And here we are considering the financial products markup language.
Okay.
Okay.
This was the talk.
Thank
you for your attention.